I'm delighted to be spending the next 55 minutes in this beautiful companionship, but they are much more than that. Everybody here is a leading scientist in their respective fields, and all related to quantum. You studied robotics, I believe, right?
Yes, so I wouldn't call myself a leading scientist, an investor maybe, but not a scientist.
And we'll get into that, and we'll explore a little bit what quantum is, what everybody is doing, and why that's so exciting. And I'll start with you, Ilana. I'll go over to you, and because you finance everybody, we'll finish with you. So quantum is spooky, right? And we were just talking about that. That's what Einstein said almost 100 years ago. And it's still not really sure when you read the press or online what quantum can really do and why and when. Ilana is building a quantum computer with her team, Oxford Quantum Circuits. It is, I had the privilege of seeing it virtually. In my opinion, the leading quantum computer in Europe, and that is a lot to say. Lucy, tell us, why does she have a name? I don't know any other quantum computer with a name, at least not in market. But what is Lucy? What is her goal? What is her mission in life? What does she want to achieve?
So Lucy was Europe's first quantum compute as a service that was available via public access. So it's an end-to-end system. She's absolutely stunning. She looks like a beautiful chandelier. She's got an 8-qubit processor. And I'm going to be honest, she's really old now, and she's going to be taken offline in the next few months. And we're going to have a party to celebrate all the work that she's done. But yeah, we build these quantum systems. They're absolutely stunning. And then we make them available to customers so they can run algorithms on these end-to-end quantum computers. And that can be through public access. It can be through private cloud access. And Lucy is paving the way for our next generation systems, which are called Toshiko. And I'll come to the name in a moment. And Toshiko is a 32-qubit processor, and these systems are now deployed in co-location data centers around the world into the world's existing digital infrastructure so that customers can securely access quantum as if it's effectively on-prem without needing to physically buy these incredible systems themselves. So this is, first of all, like very much the future of compute. Why are they called Lucy? Why is it the next one, Toshiko? Each of our systems are named after pioneering women in STEM. So when we talk about Lucy, we're talking about Lucy Mensing, who was a pioneering German physicist, and this was, of course, representing the system going online in Europe, and that being a European first. And then Toshiko has been installed in the TY11 data center in central Tokyo in Japan, and is named after Toshiko Iwasa, who is a pioneering female physicist, actually the first one that was awarded a PhD formally in Japan.
And so you're the CEO and co-founder of Oxford Quantum Circuits. You have a PhD in physics from the University of London. I'd like to go a little higher up before we talk too much about product. If Lucy looks back at all her children in 20 years from now, what will she be seeing and saying? Why are you doing this? Like the big picture.
Why am I
talking about use cases?
Yeah, of course. I mean, I want to build a brighter future for everyone that is enabled by quantum. That's very much our reason for being. That's why all of our team work for us, is they see this, the impact and the good in the world that quantum can bring, and we want to be part of that. And as a CEO, I take a huge amount of responsibility for that vision, for that mission of making sure we deliver this incredible world-changing opportunity. There's so few opportunities that you get in life to do something that's genuinely going to have an impact. Like, I genuinely just feel privileged and humbled to be able to lead a company in this way, but also bear the responsibility of that, of want to make sure, number one, we may bear the technology to full fruition, but number two, we do so in a way which is ethical, which is sustainable, which is promoting diversity and inclusion and building that brighter future, not just from the tech, but from the business perspective as well in everything we do. And I know that, you know, we have many shared values, and if we look at the other leaders of this field that are pioneering this forward, it's phenomenal to see the alignment of that, of a brighter future for all through business. And I think that's very powerful. And it's through love, but we can touch on that later.
We will. And there's only a handful of companies in Europe building quantum computers, so these are in market, they are available. They don't do all that much yet. I'll let you correct me later, but you know, this is a real thing. Of course, this serves a computational purpose on a computer, and that bigger business problem, you have a lot of information. and that's where Carmen does some crazy things. You have a PhD in quantum information from Cambridge. You're the CEO and founder of New Quantum.
Mm-hmm.
Can you explain, because I didn't really know that for a long time, what quantum information is and why you're doing stuff to quantum information and why that is so crazy? And then we'll talk, then I'll ask about product and those, but stay high level for.
Let's get right into quantum information. Well, I think, the concepts behind quantum information, quantum mechanics and quantum foundations, which are some of maybe the most successful theories that physics has ever made. And by successful, I mean they've been proven to be correct to very, very, very high degrees of accuracy. Basically give us a few concepts that make us think about information in a different way, think about information and use information in a different way. So specifically, the two main quantum concepts that we use in computing and in other areas of quantum are entanglement and superposition. So, we're not using information in a binary way anymore, where bits can be 0 or 1, but a combination of qubits or a qubit can be in multiple states at the same time, in a superposition of these states, and bits are not independent from each other anymore. They have this correlation called entanglement. And those concepts are what enable quantum computers to be so powerful. And it's this big departure in how we think about information, which is really, I think, is the significance behind this field that it's the first step change in information technology from, since the birth of classical computing.
And explain a little bit why it is so difficult to work with quantum information.
It's very difficult to work with quantum information because quantum states and qubits are very fragile. They are very susceptible to anything that happens in their environment. And we can only observe quantum mechanics when we are looking at very, very small scales, at things like individual atoms or individual ions, or things that don't interact with the environment very much, like photons, which don't have a mass, so they don't interact with the environment very much. When we try to scale up these systems, it's very hard for the world, noise and electromagnetic waves not to interact with these qubits and make them do other different things that you didn't want them to do.
So what products, what does that mean for the end user? What is New Quantum trying to make out of all this?
So what that means is essentially that because qubits are so hard to control and to isolate, and they make a lot of errors, the field has come up with this thing called quantum error correction, which means that we can use many, many physical qubits that are noisy to encode one logical qubit that is not susceptible to noise anymore and should be a perfect logical quantum entity. But what that means is that if we want to tackle commercially relevant problems and say we need 100 or 1,000 logical qubits, but we need about 1,000 physical qubits to encode one logical qubit, then suddenly the requirement for physical qubits goes to millions. And at the moment, companies are able to more or less assemble and control maybe 100, maybe less, and there's no clear path to getting to millions of physical qubits in a single quantum computer. So that's where New Quantum, the company that I run, comes in. We're building quantum networking hardware technology so that we can interconnect many quantum computers together to enable distributed quantum processing and to get to those millions of physical qubits. So we can scale in a modular way. We can have smaller, more robust quantum computers that work together in a network.
So we have quantum computers, we have the improvement of those quantum computers and networking them. Horizon tries to enable people to use these quantum computers today and in the future, right? You're the chief science officer. You have a PhD in physics from MIT, another small school that I easily got into. Tell us a little bit about what this means for the end user today, and project yourself out, whatever timeline you think makes sense.
Right. So quantum computers rely on quantum bits that Carmen has just explained to us a little bit about, and why they're so difficult to operate on and to handle. And Ilana has a quantum computer, which we call an all-purpose quantum computer, where basically you can utilize the rules of quantum mechanics to operate on these qubits and perform computations on them, called quantum computations, using gates and stuff. So, but the problem with quantum computers is that not just, of course, there's like barriers to use of quantum computers because of the need for a lot of qubits. And today we still do not have enough qubits. But there's also another barrier, which is the barrier to having algorithms that you could actually run on these fault-tolerant quantum computers. So even if we have a working quantum computer today, we still do not have the programming language, we don't have the abstraction like we do for classical computers to be able to deploy, like code, compile, deploy to quantum processors, and that is a challenge. So what we do at Horizon is we believe that it is possible to have a unifying programming language and automated algorithm synthesis to be able to construct and identify places where speed up in computations, which is a key application of quantum computers, and why so many companies and organizations are pumping money into quantum computers to be able to speed up computations that are so important to us today. So we are building this compiler that will essentially automate this process and allow our users without quantum knowledge to be able to figure out what kind of domain-specific applications they might be able to speed up using quantum techniques, but without the PhD, or PhD optional, like we like to say. Yeah, but it's a really interesting time for quantum computers. So, yeah.
Good. We'll get more into the use cases, but and these are all world first, right? As I said, there's maybe a handful of credible competitors to Oxford Quantum Circuits. I don't think Carmen really has competitors. It's too difficult what she does.
No, there's a couple.
Yeah.
A couple quantum networks.
And using quantum computers is, Einstein would definitely call it spooky. But then you have to finance all of this, and that's a lot of money. Well, actually, not that much, but more than I have in my bank account. And you understand this stuff. You have your PhD from Oxford, but venture capital is in itself a spooky thing, right? How do you make sense of this? And in the context of how venture capital works, you need to assess risk, you need to understand your return, your timelines. Tell us a little bit why you're in quantum today and how you make sense of this.
Sure. So I'm Manjari Chandran-Ramesh. I'm one of the partners in Amadeus Capital Partners, and we're a global technology investor. We've been investing for 26 years in what's now called deep tech, and it's really cool to sort of be investing in deep tech now. But Amadeus decided to invest in deep tech before it was cool. In the same way that Amadeus and I decided to invest in quantum before it was cool to invest in quantum. So I wasn't with Amadeus at that time. My first investment into quantum was actually in Oxford Quantum Circuits in, 2017, I think?
Yep.
Yes. And then I moved to Amadeus 2 years ago, and I work very closely with New Quantum. So I'm in this unique position that, I get to interact with fantastic founders like Ilana and Carmen, and I've been on many panels with Joe's and you as well. So it's a really exciting time. But to answer your question, why does venture capital look at it? So as a deep tech fund, we are really focused on the next wave of technology. And when we are looking to deploy money, we are looking for opportunities that are going to literally change the way the world is. So it's going to be a super disruptive technology. It's going to have a huge market opportunity, but it is going to make some returns because obviously we are deploying money for returns. So the timing of it does matter immensely. So when both Amadeus and I decided to invest in quantum, one of the things that we were very aware of was that the right time to actually get involved? Because you can't really time any market. Any person who invests in the stock market will tell you that. Do not try to even time the market. And that's not what we're doing. But you can take a very educated guess on what are the technical risks that need to be overcome for this to become a product. So how long is it going to be before this is actually a product in the market? What is going to be the value proposition if such a product exists? And so that's where our expertise comes in, because we've been doing this for so many years to really look at when was the right time to invest, how much should we invest. It is hardware, it is capital intensive, much more than what you might invest into a B2B software play. But my goodness, the results are just so exciting. So, no regrets on getting into quantum.
How excited are you, and Amadeus Capital does deep tech, as you mentioned, right? And we've worked with you, probably the most sophisticated VC in that field. How excited are you about quantum versus other deep tech technologies? Rank it.
Personally, I'm super excited, and I've got a huge bias on that because I did my PhD in machine learning, and I invest in sort of foundational AI and quantum. So I kind of believe that AI and quantum is the way forward. My colleagues keep me more grounded, so that's a good thing. So Amadeus itself invests in everything from sort of synthetic biology and med tech to novel materials and climate and photonics and quantum and AI and cybersecurity. But because I work so closely with the quantum startups, I think we're really at that sort of shift, right? So 7 years ago, it was definitely very exciting. It was the right time, I felt, for the technology to be funded to come out of the lab. But now, it's like it's got to a point where it's really exciting. A lot of companies are willing to engage with the startups, to look at the use cases, to work more collaboratively to actually create a product. And I think that's a fantastic time for startups, for investors in these startups, but as well as the large corporates, because you're actually in that process of bringing something that was possibly science fiction, or at least definitely in the lab, out into the market.
And we are in the process of bringing these technologies to market, and users are starting to use them. And we're also in the process of figuring out business models, pricing models, all these kind of things. I'm sure you all have heard about IBM and their cloud offering. They now have 24 quantum computers available in the cloud. And I live in the US, that is the approach there. Lucy and her children have a different approach. Can you talk a little bit about that and why Oxford is taking a different perspective on how to bring that hardware to market, and why you think that is better?
Yeah, absolutely. So first, I'd probably say that her sisters, and they're probably her bigger sisters rather than necessarily her children. But what we're doing is partnering. So we have the strategy of building the core and partnering with the best. Like, we cannot expect to have to do everything ourselves. That's why we have partnerships with some key people here as well, to make sure that we can provide the right service offering to customers. The way we see this market evolving is much more like, say, the high-performance compute market before it. So if you look at the standard McKinsey, 15-year projections, like 260 billion. And if you look at the high-performance compute market, that's segmented into two. So you had one area which was like exclusive, kind of very high performance but niche, like lab-based quantum. High-performance compute analogy might be to say Lenovo. And then you've got more mass market, widely accessible quantum, which is, say, more like Dell. So for OQC, we're focused on that kind of Dell as a service type model of making sure we are providing quantum to customers in a mass market accessible way. Now, we cannot expect those customers to come to us, right? We cannot expect those customers to go, right, I want to engage in quantum. I have no idea what I'm doing. Hey, I'm going to have to go to my chief information officer and now say, that little startup over there, can I put all of my private confidential client data across the public cloud and run a quantum algorithm in the middle of Oxford countryside? Like, it's probably not going to happen. It's a huge barrier to entry of access. So instead, what we focused on is how can we make sure that we are creating this vision for enterprise-ready quantum, which is focused on customers today and bringing quantum to their existing infrastructure. And that is enterprise-ready quantum in a nutshell, right? It's seamless, it's 24/7, it's integrated into their existing workflows, be it through plugins, be it through their existing data center models. We approached Equinix, which is the largest data center provider in the world, about this, and they completely got our vision, and it was with them that we thought, right, let's now physically deploy the quantum computers into these data center environments. That means that everybody that has either a rack in those data centers can direct connect into those systems, and literally you can log on to the platform and just search quantum, you find JQC, and you just add Toshiko to the system, right? That's not to say that QCAS, Quantum Compute as a Service, isn't the primary business model in terms of go-to-market strategy going forwards. What we're doing is then strategically positioning ourselves around the world in the locations where the customers are and bringing down their barrier to access as much as possible. The other thing I'm super excited about is, right, think about the different market verticals. What software applications already exist where quantum is going to be a huge enabler? For example, simulation software. Think about stuff like ANSYS or any type of modeling. The financial markets, what's their software that they're using? How can we integrate quantum as a plugin into the back end of that so it's seamlessly accessible? Ultimately, the customers, they don't care that it's quantum computing. We don't want them to care that it's quantum computing. We want them to be able to just solve their problems in ways that has never been possible before. And that's really what we're doing in that go-to-market strategy. I think, of course, it's nascent. Of course, it's early. About 4% of the market, I'd say, are advanced. They come to us, they're like, just give us access to the computer, give us the API. We've got a team of 25 plus engineers that already know and are analyzing. And this is primarily defense and security and financial institutions that sit in that kind of 4% of super quantum advanced that can just get on with it. About 70% are early movers, and they are engaging, but they need a little bit more support. They need a bit more hand-holding through it, and that's where we partner, and we have relationships with other consultancies or other quantum software companies to support customers on that journey. And the final area, of course, is then the people that just want business impact now. And that's a really interesting area. And actually, we do have customers that are like, I just want business impact now. And quantum is never going to be siloed, right? It's never going to be just you're running a quantum algorithm on its own. It's going to be integrated into the existing world. You're going to have QPUs, GPUs. Like it's going to be integrated with high-performance compute. So here, what we're able to do is partner with Fujitsu, partner with NVIDIA, and then find what subsets of algorithms can you run on quantum computers, and then how can we make sure we're still delivering business added value now through the high-performance compute aspect, so that you can get them on that journey, but also provide them the business added value, which demonstrates return on investment for their key stakeholders internally as well. So that's the market today and how we're navigating it, but the future is still quantum compute as a service. That's the value inflection point, and it's just how do we make sure that we support customers on that journey to get them through that pipeline, bring down the barriers to access, and then make sure as a company we're strategically located to service as many customers as possible around the world.
That's a bold statement, quantum as a service. I'd like your opinion on that. But before, you're absolutely right. People don't buy quantum, right? They don't really care. What is the mindset of a buyer? And I'm not yet talking about use cases. We'll get there next, hopefully. But what problem do they have? What's going on in their head that they say, hey, we need to call Oxford quantum circuits?
It kind of depends, and spoke about this kind of advanced versus early movers to what their mindset is. Generally, there's a huge amount of FOMO, right? There's people that recognize that quantum is going to happen. It is inevitable, right? There's enough technological development, there's enough money in the market, there's enough traction. Quantum is inevitable, genie's out of the bottle, it's going to happen. And quite a number of people have been ahead of the curve on that and have already started putting the teams together. So they've already identified specific use cases, say within their portfolio analysis or within their specific, not getting onto use cases, getting within their specific area, they've already identified, and they are of the mindset of, I just want to be able to prove this out, understand how to work with the system, and make sure that I can also assess and benchmark the systems that are out there today so that I can get there first. Super competitive. The second lot, usually there's one or two people in the organization who have been tasked with, we need a quantum strategy and we need it 3 years ago. And they've been tasked with that, and they've got to figure out the market on their own. They've often the first question I get is, I need a team. What team should I build? And I send them someone else. But it's often with them it's more curious. It's more trying to understand the impact on their business, what sort of subsets of problems it can solve, and it's often quite like an educational journey for them to understand how to interact with it and what it's going to mean for them as a business. And usually they're kind of middle management on rapid career progressions that have got this opportunity to build out a quantum strategy and a quantum team and recognize the potential of that. So I'd say that's the two general kind of approaches.
And so Ilana made this bold, in my opinion, claim that the future is quantum as a service. There are many other models, right?
Yeah, they make us more money today, but
I'm not going to pick that fight. I learned my lesson. Don't argue with Ilana. But hopefully you can. IBM just offers a cloud, hands off, and they have a consulting team, right? Others just do on-premise. There are many different business models in quantum that are emerging, which I'm sure you look at with Amadeus. What's your opinion as you look at the ecosystem and they are starting to come to market?
So I think that is the beauty of a nascent landscape, right? You have this option of exploring various business models. I mean, even when SaaS came about, there's so many different business models, ranging from the freemium to the enterprise, licenses. So I think that is a really good thing, that there are so many different business models. I'm not going to predict where the market is absolutely going to land, because I think we're still in a stage where people are trying to work out where they're going to fit the whole quantum offering into their business processes, where exactly they're going to. They have certain ideas, which is great. They are testing those ideas, whether it's the financial institutions or indeed, sort of new materials, the pharma sector, they're all testing. But until there's a clear pathway that this is exactly where the value proposition is, we're not going to really know which business model is going to fit that value proposition. So I think it's great that each company is trying out different business models. That's exactly how it should be, but we're not going to call it right now.
Yep, too early to call. I can't really call you and order a pound of entangled photons. Your market is a little different. Your customer is very different. How do you view that maturity of the market in general, but your technology and your products specifically? Who's the buyer? Why are they buying it? And what?
Yeah, it's an interesting question. So just as background, quantum networks is at a much earlier stage than qubit technology, than quantum computing companies. So there's, as we were saying before, there's 70 or 80 qubit companies building quantum computers. There's fewer than 5 quantum networking companies in the world. And we're getting we're building the first prototypes, whereas, Ilana is already deploying, I don't know how many quantum computers all over the world. So, so it's a little bit more early stage. And the business model or how we get income will change over the next few years. So for us, we'll start to deploy the first systems to buyers that are government and some big industry that is interested in exploring what it means to have this capability, this networking capability, this distributed compute capability, and what needs to start to be built on top of that. That will be the next, several years, maybe 4 or 5 years. We will start to also kind of, collaborate with qubit companies as they come to their limits of scaling and they start to need to explore what comes after and start to build prototypes of distributed computers. So, hoping that will happen soon, for example, with OQC and others. And that, again, will be first prototypes that will be very, very high-value systems because they will be very unique and sold to government, big industry, maybe some deployment in data centers. The roadmap for qubit companies is all about, having more and more qubits in their systems and higher performance, lower and lower errors, and more availability, which is a big thing. It's a big challenge in the industry. For a quantum networking company, the roadmap is all about being able to interconnect more and more nodes, even if each node doesn't have that many qubits, but connecting a larger cluster with, again, higher performance, which in our world is all about rate and fidelity. At some point, these two will come together, and that's where I see the kind of as-a-service model really taking off, because we will be able to together offer much more compute capability and much more service quality. So things like uptime. If you have a modular system, if one of the nodes has a problem, you can keep using the other ones. Things like elasticity of service and robustness of service, those are things that we can aim for when both networking and compute roadmap come together. When that will happen is $1 billion question, but I should think that it's the kind of 5 to 10 year side of the decade.
And I don't think we have yet done justice at the scale of the impact that your solution could have when it's deployed. In very simple term, when I eat ice cream, I'm less sad. I drink wine, I'm more happy. What is the scale of the impact when your solution is deployed? Why is that so meaningful?
It's meaningful because it tackles scaling in a different way. So not relying on more and more R&D breakthroughs inside our computing core. We already know there's very tough challenges to continue to scale the number of qubits that you can reliably control. So you have it's a tangential way of scaling that is modular and can provide that that path to commercial fault tolerance, really, where we could ideally stamp out robust, smaller quantum computing cores and interconnect them together in an interesting architecture. And then the other thing that is very recent for us, but I think really exciting and potentially really meaningful, is that, so we were talking about error correction before and the fact that you need many physical qubits to encode one logical qubit. So the reason you need so many physical qubits to encode a logical qubit is to do with how the qubits are arranged and how they are entangled together. If you have a single node, that pattern of qubits will be static. It will be what it is, usually nearest neighbor connectivity. If you have the ability to entangle cores with these photonic links, you can create a pattern of entanglement, a topology of entanglement that is not fixed. It's not nearest neighbors. Is something maybe more complex and more long range, more like a hypergraph rather than a 2D plane, and that could allow you to use better error correcting codes that need fewer physical qubits per logical qubit. And long story short, you might need fewer physical qubits to get to the same computing power that was predicted with just monolithic scaling. So a more efficient architecture could be achieved with a distributed system.
Yeah. Nobody wants to build more qubits. The fewer qubits we can do, the better, right?
We want more qubits. We want higher quality, higher performance qubits. But we do definitely need to scale. And interconnects is 100% one way of scaling. Yeah.
So we're still not exactly sure what customers actually want to do with it, but you're selling it to them. So you do applications, and we'll talk about use cases, but help us understand what that looks like. Who comes to you? What do they
Right.
ask for, and what do they get?
Yes, we are focused on not like specific applications for quantum computing. So what I mean by that, I have to step back. To explain that, I have to step back a little bit. So I mentioned that, you know, for applications, we rely on specific algorithms that have been discovered. And the types of algorithms that have been discovered revolves around, you know, like creating crypto systems, search. There's a Grover search algorithm. You know, then there is factoring, which, you know, breaks RSA if we have, you know, one day a fully fault-tolerant quantum computer. And more recently, in the last 2 decades, we have HHL, which is a quantum machine learning algorithm, which also has an exponential speedup. So I mentioned exponential speedup, and the fact that quantum computers can do these things much faster than classical computers, or at least promises to, when it finally comes to fruition. If we one day have Lucy at 1 million qubits, it can do all these things. And that's the kind of applications that have been discovered. But what we believe is that because very few people in the world today could actually create these or find these algorithms, because they're, you know, siloed into domain-specific knowledge. So we think that, we at Horizon think that there's a lot more applications out there that could lie dormant for us to discover, or at least, you know, something that nobody has thought of, right? And in fact, the 3 domains I talk about, it's like 3 large families of algorithms, quantum algorithms. And in fact, recently there was a result that says that, you know, these can be framed into one problem, which is the quantum singular value problem. But anyway, so what we do believe is that, you know, if we put a quantum computer in the hands of developers who are trying to find applications to speed up their calculations using quantum computers, they themselves, you know, could actually discover more about what could be done. And we think that applications can be as wide-ranging, you know, as high-performance computing. And that's how we think people should think about quantum computers. It's not, you know, oh, okay, you know, something completely crazy and new. It's like, actually, you know, we have things today that analogously can be thought of as, you know, like high-performance computers. And quantum computer, I think this also kind of rings similar to what Ilana said, you know, like, it's like, it should be sitting in the server. We shouldn't think about it as like something completely crazy, even though maybe quantum mechanics is, but it's something that could potentially speed up a lot of different calculations that is inside applications. And it's just that it's waiting for us to discover that. And we think that the way forward is not for, you know, like a company to go to another company and say, hey, can we pay for a PhD student to look into this, take months and months to come up with a quantum algorithm or like a variant of a quantum algorithm to speed things up, but rather, you know, do it automatically using known techniques, maybe in quantum techniques, but it could also be classical techniques. And I think that's interesting because like the emergence of quantum computing as a resource now, right? So you can deploy through AWS or Quantum or, you know, IBM. You find that like when someone, you know, runs something on a quantum computer and say, oh, I got this, and it's like kind of there's a speed up, and then like the classical quantum computer science is like, no, we can't be beat, and then they find something better. You know, they find an algorithm that's better by like tiny little bit, and they're like, see, you know, like so it's actually pushing the frontier of computer science, and not just you know, among quantum computing scientists.
So what does a happy customer today look like? Do they go home with millions in cost savings on whatever process you worked on, or in your experience, what is success today?
Right. I'm getting a lesson in MBA here, but so we are still pre-launch at Horizon. We are pushing early access soon. But we don't have customers yet, so we're still trying to get our system built and up and into the hands of customers. But I think we project potential customers, once we have the system built, to be people who are interested in high-performance computing, so probably things like aerospace industry, probably automobile, you know, people interested in molecular simulation, so pharmaceutical companies, people interested in, you know, fast computations, so banks, and you know, a few others probably like mining companies who might want to compute certain simulations quickly when they try to do, I guess, geomapping or stuff like that.
Yep. So Manjari, good news. I'm very excited. I just decided to build a quantum computer, and I'd love to accept you as an investor. How big a check do you need to write to me for me to be able to do that?
Before I go to that, I'm going to just cover one more point about the business models, right? So we spoke about business models for the quantum computer itself, but as Carmen said, as a quantum interconnect, the way they charge the customers is going to be quite different because their customers are going to be different, right? And if I look at some of the other companies within the portfolio, so Riverlane is doing, it's the operating system for error-corrected quantum computers. Their customers will be the end customer, but also somebody who's going to be working in the landscape. So their business models is likely to be slightly different. And then if I look at yet another portfolio company called CryptoSense, which got acquired by Sandbox AQ, they're actually looking at post-quantum cryptography, how if a quantum computer was there and able to crack your current encryption methods, what do you do? So again, their business model is going to be very different from what quantum computers' business model is going to be. So I think that's the excitement of such a nascent landscape in that there are so many different ways you can actually approach it. Going to your question, I think this is like any other sort of deep tech investments. It needs patient capital. And I always sort of tell my founders, Carmen's probably going to go, yeah, I've heard this now. When you say patient capital, it's not the lack of progress. It's just it takes longer to find that product market fit, right? In sort of the non-deep tech sectors, typically you'll come to a minimum viable product 6 months, maybe a year. You're already deploying it. I mean, these founders have been working on these problems right through their PhD and as a company for several years. And it's only now that it's actually coming to the market. And it's that kind of understanding as a deep tech investor that you need. So it's not, I wouldn't say it's necessarily amount on the check that is the thing that decides whether the right investor is in the right company. I think it's very much the investor who understands what it takes to get to product market fit, what it takes to actually scale the company, which business model is going to ultimately work for the company.
Yeah, and there are companies that have raised 40, 50 million and built a working quantum computer.
Companies that have raised several hundred million as well, right?
800 million, yeah. And they still don't have a working quantum computer.
Exactly.
So it's difficult to say. A company just sold 2 quantum computers for, I think, 21 million. To some people in Switzerland. Was it 21 million? So if you do the math,
I need to up my prices.
Yeah, right.
Yeah,
it's a good market.
I think that the point here, though, is more money doesn't necessarily mean a better product, right? I think it's a mistake for the market to think that that company has raised 300 million. They must be the best quantum technology company out there. No, they've been very successful in convincing investors that their vision is something that the investors should buy into, which is a skill in itself, right? I'm not, sort of detracting it from the management team, but that doesn't necessarily make their tech the tech that's going to win, right? That they have a very good chance. It's a lot of money. You can do a lot of things. You can make some mistakes and get away with it, which you can't do if you don't have that much money. But it doesn't necessarily mean more money means the company's better.
Yep, there's still a real advantage in smart science, smart engineering in this space. So, and we have 10 minutes left. I think we promised backstage to have a positive, uplifting message on this panel. No doomsday, AI or quantum. If we look at the future, and you decide what that future is, if it's 5 years, 10 years, 20 years. But I still don't feel we've really honed in what quantum can potentially do and how it can change the world. So I'd like to go down the round and give us your dream, the uplifting story.
Well, I think, as we were saying right at the beginning, this is the first kind of step change we've seen in, the processing of information since classical computers. So we're kind of, I think we're at the beginning of, the next century or centuries of this really giving fruit. So, there's the possibility that these technologies will end up delivering as much value, as much new use cases, and as much benefit to society as, the first wave of classical computers and telecommunications have done. That's, that could be a world in, several decades. For me, one of the areas of application of quantum that I think is very interesting and has the most impact potentially is everything to do with climate change and the new materials and processes that we will need to really, really, really change the way we occupy the world.
For you, is it a dozen use cases in a dozen different industry, which is huge, of course, that would be transformative, or is there a bigger mission behind it, maybe as well when it comes to the application of?
Yeah, I think the ambition is high. I think we want to think of quantum computers as something that can change the way computing works now. I'd like to just point out the pattern in this. It's like, quantum technologies is not an old thing. It's not, magical. It's just that we got to the point where, we have so much control over these tiny microscopic systems. It appears like magic, because we could actually do things with them that we couldn't do before. And, when I started my PhD, it was like more like, 2004. It's unimaginable that we would have an operating, quantum computer, sitting on AWS waiting to be deployed to. And I think, the first quantum revolution came about, some time ago was the transistors. That was like the previous, topic here on the stage. And then the second revolution, I think, was things like GPS, lasers, which, you can't live without a laser now, right? And that's essentially a quantum mechanical process that happens, but you don't think about it. And I think this is part of that pattern, it's like the third wave. And, it's about information, which is exciting, being here in England, Shannon, Turing, all the big ideas about computing and changing the world. So I think, implore everybody to think big, and that, this is, something that we all can have a share in, and potentially, be optimistic about what the technology can do for us. And we hope that, we will do it for good and not for otherwise.
Version N of Lucy?
I think what's amazing about quantum is quantum enables us to solve the problem of problem solving itself. That's the machine. That's incredible. And you can imagine this future where in 10 years' time on Lucy to the N, you're able to truly simulate and create new drugs, right? Create new drugs that underpin the future of pharmaceuticals, because each and every molecular atomical interaction is quantum mechanical, and we cannot simulate that effectively with any accuracy or for a long period of time, because it's a quantum mechanical effect with a classical computer. With quantum, you can do that. So that's huge impact on society as we know it. Take the drug discovery process down from 10 years to effectively simulating it on a processor in 10 minutes. You might imagine a future the same, like for molecular simulation. Photosynthesis happens every blade of grass around us, and we cannot simulate that process. That underpins the energy industry, right? Fertilizer solutions that are around the world use up like 14% of the world's energy. You have to do it in massively high energy-intensive, wasteful chambers under extreme pressures and extreme temperatures. Yet, Mother Nature has figured this stuff out on the grass around us. That's quantum mechanics. With a quantum computer, we can truly understand that and understand that problem and come up with better solutions. Same with batteries, right? Think about the band gap. How can we use that to create new battery technologies? And then, of course, data. There's so much data in the world, and yes, we know that we can utilize data incredibly powerfully today. We are burning up the data centers from an energy-intensive perspective, solving these complex algorithms, and we're still limited in terms of the multivariable problems that we can solve. With a quantum computer, you can solve these multivariable problems a lot more quickly, a lot less energy-intensively as well. So we can help build that brighter future. This is what we're talking about. This is a brighter future for all. And once you have a system that is truly powerful enough, and it's not simply an imagined future of 15 years, this is already happening today. We have customers today. I'm doing flood analysis, seismic analysis, Monte Carlo simulations, radiation transport modeling. We're doing all of this work with large corporates already today. We're working with financial institutes on understanding what algorithms they can do to, better understand their risk analysis. Yes, it's a little less like green and fancy, but these are applications that are happening today, and we're just at that tipping point where the next generation of systems that we're going to see deployed within the next few years, and I would say even probably potentially from some people's roadmaps at the end of this year, beginning of next year, we're going to see that space where you can no longer simulate the quantum computers with the existing, multi-core processors. So that will be truly the point where we've actually been able to achieve that transition point. Some people argue we've achieved it already. Some of our customers say they've got speed-ups already. I'm like, because it pushes the algorithms to be better. So it's such a pivotal moment for the space, and I'm so excited about the field, and I hope that gives a snapshot as to why we should be optimistic for this brighter future for all.
Is there a quantum company out there that you haven't come across yet that you dream of? If Amadeus were to give you 100 million, 20 years, none of your partners asked for any accountability, carte blanche, I'll build it. Tell me.
I'm not sure that, one company is going to be a winner takes all. That's not the quantum landscape, right? So, if you look at the market opportunity by whatever it is, McKinsey or BCG, even their report, the one that came out, I think it was in April, was the quantum computing market will be anywhere between 9 billion and 93 billion. Like, what kind of a range is that? Because it's just so difficult to actually say this is going to be, sort of exactly this market, and it's going to be this company that's going to capture all of it, or 90% of it, right? So if I had 100 million, I would definitely invest a lot of it in the quantum space, but it would definitely be across the landscape.
Good, smart portfolio approach. I love that. With that, quantum is coming, and we are all very optimistic about it. For me, the key message, what these 4 entrepreneurs, and VCs are entrepreneurs in my book, are doing is something new. They're not working on improving an existing thing or making something a little bit better. Everything these 4 are building has never been done before, and they are the world best at it, which is really pretty fascinating. So thank you so much, Ilana, Manjari, Si-Hui, and Carmen. I think we have a couple minutes for questions. Can't really see in the light, but I do see a hand. I see 2 hands. We'll start in the back on the couch, if that's okay.
Yeah. With the design space, and I saw, with a quantum computing, you can put all the design space at once, and they will deliver the optimized design in terms of process, in terms of material. Is it a bad picture?
Yeah. So to summarize, and of course anybody, but Si-Hui, I think it's for you. It's a question about optimization, especially in product design, and you come out of machine learning. But is that something that's possible? We have a product, we want to design a new table, and then instead of bothering a supercomputer with it, a quantum computer can just give us the optimal table.
There are algorithms out there that basically tells you how to use the quantum computer to, or at least quantum processors to find the solution to your problem. Yes, but yeah, right. Yeah. So the answer is yes, but it depends on what kind of optimization you're looking at, and whether or not there are promised speed-ups there.
Yeah.
From like a physical cost perspective, the current QCAS model that is available is broken. If you want to start doing actual, like, large-scale algorithms, it would cost you like £4 billion or something to do a useful algorithm at a large scale. It's been set by the incumbents at like 0.00035 pence per shot, but realistically, that doesn't make sense when you have algorithms with many multiple shots across a probabilistic space. So that is something that we're also pushing down, right? So how can we give discounts for large volume utilization? The business model does need to change. The future is QCAS, but the costs need to come down to make this viable for the long term.
All that remains is to thank our brilliant speakers. I'm afraid we don't have time for any more questions, so we have to end on time to let workers go home. Thank you so much. It was absolutely fascinating. I'm sure I speak for all of us when I say we learned a lot.
Thank you.